Okay, so this is just finishing up on the experiments. There's a couple more types of experiments, and then there are just the three principles that we need to discuss. So the three principles of experimental design are control, random assignment, and replication. The control can mean both a control group, or it could just mean, and it could mean controlling other factors in the experiment. So if you think about the caffeine example that we had yesterday, obviously for the control, we would want a control group. So we want a group that is drinking a caffeine-free cola. But if you think about it, there's other things we'd want to control too. So maybe we'd want to control the amount that they get. We want to control the temperature. We want to control the color of it. We don't want to give like Mountain Dew to the caffeine group and then like, you know, Coke free to the caffeine free group. That would be like kind of apparent that who was drinking what. So we want to kind of make it look as similar as possible. So you're not swayed by something. We can also control when we take the pulse rate. So we want to make sure we measures everybody's pulse rates after the same amount of time has lapsed. We want to make sure that we're using the same instrument when we're measuring everybody's pulse rate. The random assignment, so subjects will be assigned randomly. Ideally, if I could get a random sample too, that'd be great. But let's just say I have, students, so then the only thing I can do there is do the random assignment. And then replication, each treatment is going to be applied to 15 subjects. So I'm just repeating this procedure on 15 subjects for each group. Yes, the more you can repeat it, the more accurate results are, but at the same time, we don't always have infinite resources. Replication also, I mean, obviously one person isn't going to be enough. There are certain types of experiments, especially like in the medical field when you're testing procedures like surgeries or stem cells or things like that, that maybe you are going to have really small sample sizes. All right, before we get into some of our other designs, so what else can go wrong? So there is something called a placebo effect, which is just a response to a dummy treatment. So you just think you get better, or you say you get better, or you feel better, or whatever, but really you actually had a sugar pill or no treatment. So here's a little thing here about more expensive placebos. You can read that. You can pause the video and read it. The double blind, so double blind would be that both the subjects and the person administering the treatment doesn't know. Obviously, somebody somewhere has to know what's going on because somebody somewhere has to be, in charge of what Coke. Like if I go back to the caffeine experiment, somebody has to know which cup has the caffeine and which cup doesn't have the caffeine. But they can just be labeled like A, and then the other ones are labeled B. So the person in charge of the experiment might know, but then the person delivering the cups of soda doesn't know. So the person interacting with the subjects and the subjects themselves don't know what treatment they're getting. In single blind, only one doesn't know, and again, it's generally, obviously, the subjects that wouldn't know. Could the caffeine experiments be double blind? Yeah, of course. So again, I could set up 15 cups with caffeine and 15 cups without caffeine, and I could label them A and B, and then I could just hand them off to somebody else who's administering. I don't have to tell the administrator which one has A and which one has B, and then they just, give the cups to the subjects. All right, statistically significant, what does it mean? So statistically significant is an observed effect is so large it would rarely occur by chance alone. So if you think back to our first day, we had that activity with the hiring discrimination. And when we were looking at that, we simulated what was the likelihood of getting 5 females out of 8 pilots selected. And we created a dot plot, and then we looked to see if we thought it was unusual or not. And we said it wasn't unusual. And then I went on and I asked you, well, what if we would have gotten 6 pilots that were female out of 8? And I don't think anybody had any 6 females. Maybe there was one person that had something. But again, so it could happen, but it's unlikely to happen by chance alone. So if it's unlikely to happen by chance alone, something's called statistically significant. So what does it mean? It means that a well-designed experiment, if the experiment was well-designed, then something caused the result. So if a drug manufacturer says that a new drug produced statistically significant results, then that means that that new drug had some sort of improvement over the prior drug, and that improvement that they observed was unlikely to happen just by chance alone. All right, so then we can break it up. So we did just regular completely randomized design experiments, but then we can also do block, or we can do something called a match pair. So a block. A block is a group of experimental units that is known to be similar. So they share some sort of characteristic. And I believe that that characteristic that they share is going to react differently to my treatment. So maybe I think men and women are going to respond differently to my treatment. So what I might want to do is block. And then basically what I do is I randomly assign the treatments within the block, okay? Control what you can, block on what you can't control, and randomize to create comparable groups. So block on what you can't control, and you will see this in some of these examples here. All right, so this example right here with chocolate chip cookies. So basically what's happening here, we have a baker, and she's obviously not only a good baker, she's also a very smart baker and really appreciates her statistics knowledge. So anyways, Anne is an avid baker who would like to compare 2 different chocolate chip cookie recipes, A and B. So she recruits 10 volunteer taste testers to rate each type of cookie on a scale from 1 to 5. She will make 10 of each type of cookie for a total of 20. Each cookie tray will hold 10 cookies, so she will use 2 trays and bake them at the same time in the same oven. 1 sheet on the lower rack and 1 sheet on the upper rack. So those of you that have baked cookies before, you kind of know that there could be an issue with the 2 racks, because one rack might cook a little differently than the other rack. So we're going to use 10 locations on the lower rack as one block and 10 locations on the upper rack as the other block. So again, I am blocking here because I think cookies cooked on the top rack are going to perform differently than cookies cooked on the bottom rack. And if I didn't block, in the end, I might not know, are my people selecting cookie B because B is the better cookie, or is B the better cookie because the majority of them were baked on the top rack and the top rack just cooks better. On each sheet, Anne will randomly place 5 of each type of cookie. This way, the type of cookie will have 5 on the lower rack and 5. Each type will have 5 on the lower and 5 on the upper rack, balancing out the effect of the rack location. Note that in this experiment, the locations in the oven are the experimental units and the recipes are the treatments. Outline this experiment in the diagram. So we did this a little bit yesterday. This maybe looks a little bit different today. So we have 20 locations in the oven. And the first thing that we do is we block. So we have the top rack with the 10 locations. We have the bottom rack with the 10 locations. And then what you're doing is you're basically conducting a randomized experiment within the block. So within this block right here, I randomly assign locations to the cookies. So what ends up happening is type A is 5. Type B, I have 5. And then in the end, I compare tastiness. And then this one on here looks the exact same way. If you notice here, I'm taking the treatment and the numbers and like smushing them together in one like piece there, just because otherwise I'll be kind of redundant. I mean, I'm trying to, not redundant, but I'm just trying to shortcut how much I'm writing there, okay? All right, so some people ask me, should I add another arrowhead at the end saying I want to compare the whole overall thing? I mean, you could, but that's not really required. You could find out that on top rack, the top rack B is better, and then under the bottom rack B is also better. So then you could just say B is the better recipe. But maybe you'll find out B tastes better on the top rack, but A tastes better on the bottom rack. And so then you really can't say one's the better recipe. So then you're kind of stuck always making 2 recipes of cookies or only using 1 rack in your oven. So anyways, all right, go ahead and read the next example. This is like, you know, maybe like if we were in class, I'd say read the example and do the problem. But since you're watching a video, I'm not gonna like wait for you to do the problem. So you're gonna pause the video and then try the problem, and then you can unpause it when you're ready to listen to me again. All right, so I said here that why a randomized block might be preferable to a company. So this one, a person's text frequency may influence the type of keyboard they prefer. There would be too much variability in a completely randomized design, i.e. it would be hard to distinguish if the results were from the keyboard or their frequent texting. So I might say in the end, oh, keyboard A it seems to be better, but I don't really know, is keyboard A actually better or is keyboard A better because my novice texters, which there are more of, preferred A, so the type or texter is actually influencing the result. So what I'm going to do here is block on the frequent and novice texters. So I have my 300 subjects, a random assignment. I got type A 50, the keyboard type B 50, and so on. Then I compare the number of correct words. Okay. All right, a matched pair design is a type of block. So it is considered, sometimes people will call it like a block design because it is still kind of a block, but the block consists of some sort of pairing. Sometimes a pair in a matched pair design consists of a single unit that receives both treatments. So what I'm saying there is like, I don't know, let's say I have this person here and I'm going to test a lotion. So maybe I put lotion A on one hand and I put lotion B on the other hand. So that person is so that I have a single unit and both treatments are being applied there. Or maybe I have a leaf and I'm going to apply some sort of pesticide on one side of the leaf and another pesticide on the other. So again, I have one unit that's receiving both treatments. The other thing that can happen is I can pair people up, or I can pair things up based on something. So maybe I pair up people based on their heights. And then what I do is one person gets a certain treatment and then the other one gets the other treatment, okay? The order of the treatments can influence the response. So chance is used to determine which treatment is applied first for each unit. So what that would mean there is if I had a bunch of people like this with 2 hands, I would randomly decide which lotion is going to go in this hand or which lotion is going to go in that. Or with the leaves, I'd randomly decide which is A going to go here or B for each particular leaf, each person. Here, again, I would flip a coin or whatever to decide who's going to get A, who's going to get B, okay, and so on. All right, so in this last 2 examples right here, so I got a boot. So manufacturer boots plan to conduct an experiment to compare a new method of waterproofing to the current method. The appearance of the boots is not changed by either method. The company recruits 100 volunteers in Seattle where it rains frequently to wear the boots as they normally would for 6 months. At the end of the 6 months, the boots will be returned to the company to be evaluated for water damage. So I have my 100 volunteers. All right, so this is kind of like the little picture I drew on the other page. So like with the person with the lotion, because in this scenario right here, each person has 2 feet. So since I have an opportunity to do a matched pair, I'm going to do a matched pair here. If I didn't have that opportunity, so, you know, I mean, yes, I could take my 100 volunteers and 50 of them could get the new method and 50 of them could get the current method. But it is possible that in the end, I'm not going to know if one method is better because of the type of person or the activities that that person is involved in. Like, I'm not going to know if it's the method that influenced the results or is it the activities or the usage or whatever of the boot. So in this scenario, since each person has 2 feet, I can utilize that to do a match pair. So I can put the new treatment on the right foot for 50 of them, so they would get the current treatment on the other one, and then I can do the new treatment on the left boot for 50 of them, and then the current treatment would be on the other boot. So if you notice here, I am randomly assigning like 50 people to this group, randomly assigning 50 people to this group. And then I am not giving all of them the right foot as with the new treatment. Another thing, if you think about when you drive, you always drive with your right foot. So that boot might get overused a little bit more. So I want to randomly assign which foot those boots are going on, or that treatment. And then I'm going to compare water damage in the end. Could my design be double blind? Absolutely. So definitely, so somebody else, somewhere has those boots and they're just, labeling the boots or whatever. And that person gives you the boots and says, okay, subject 1 gets these boots, subject 2 gets these boots or whatever. And so, yes, you can definitely, the participants as well as those administering, giving out the boots doesn't need to know. Again, somebody, the person in charge of the experiment maybe does, but they don't have to know. But the people receiving it and the person giving the boots out doesn't have to know. All right, again, take a second, read this one down here, and I'll show you the answers. Again, pause, work on the problem. All right, so with this one right here, so if you notice here, I kind of follow the same idea. I got 20 subjects. I randomly assign them. If you notice here, I am not putting them all in the 70-degree room first, and then they're all going to the 90-degree room. Because if I did that, let's say that there's 2 things that could happen. They could get tired the second time, so then I don't know, are they doing worse because they're in the higher temperature, or are they doing worse because they're tired? They could also improve because they're doing something a second time. So again, are they having more insertions, correct insertions here because of the temperature, or because they're improving because it's their second time? So that's why half of them are going to go to the 70-degree room first and do it, then go to the 90-degree room. Half of them are going to go to the 90-degree room and then go to the 70-degree room. So what's happening here is each person is doing the experiment twice. So each person is serving as his or her own control. And then I just compare the number of correct insertions there. All right, that is all there is for this lesson.